In this video, I'll review the answers for the final exam review. We begin with problem 1. It states a stenography school claims that its graduating students will average 80 words per minute in diction. A sample of 18 graduates found that they average 78 words per minute in diction with a population standard deviation. So this indicates that we will be using a z-test of 8 words per minute. Alpha is 0.01. Is the school's claim correct? Well, the claim is that the average is 80. That's our claim. So the claim is H naught. For H sub 1, it's the opposite of the mean being equal to 80. So mean is not equal to 80, which indicates we have a two-tailed z-test. We can then look up the critical values in table F. So alpha is 0.01, not equal, lets us know it's two tails. Two tails, 0.01, go all the way down to the z value, 2.58. So we have negative 2.58, positive 2.58. We calculate the test point. The sample mean is 78. Population mean is 80. Population standard deviation is 8. And sample size is 18. This computes to negative 1.06. It does not fall in the critical region, so we say do not reject H naught, and then we summarize by stating there is not enough evidence to reject the claim. Okay, number 2 says the following: a manufacturer of light bulbs claims that his light bulbs have a mean life of more than 1150 hours with a population standard deviation of 80 hours. A random testing of 144 light bulbs yielded a mean of 1169 hours. Find the p-value and use it to determine whether there is evidence to doubt the manufacturer's claim. Use alpha equal to 0.05. So the claim is that the mean is greater than 1150. That's the claim. Since it's greater than, it's an H sub 1 statement. H naught is that the mean is 1150. And we're using the p-value method, thus we have to calculate the test point first. So the sample mean, 1169, minus the population mean, 1150, divided by population standard deviation of 80 over the square root of the sample size, 144. That equals 2.85. So recall, we want to determine this area, the right tail area. That's going to help us calculate the p-value. So we then look up 2.85 in table E to find the left area. So 2.85.9978, that's the left area. We desire the right area, so 1 minus 0.9978 is 0.0022. Since it's a one-tailed test, this is the p-value. So the p-value is 0.022, and it's less than alpha, which is 0.05. Thus, we reject H naught, and we write that there is enough evidence to support the claim. On to number 3. Number 3 says a grocer claims that the average grocery bill at his store is $95. A sample of 20 customers' bills showed an average of $98 with a sample standard deviation of $7. So the sample standard deviation is S. That means we have a t-test. Alpha is 0.05. Is there enough evidence to support the claim? Well, the claim is that the mean is 95. That's H naught. H sub 1 has to be the opposite. The mean is not 95. It's a two-tailed test, since we have not equal. we need to compute degrees of freedom. So degrees of freedom is 20 minus 1, which is 19. And we then look up the critical value in table F. So 2 tails, 0.05, we go down to 19, 2.093. We have negative 2.093, positive 2.093. Plug in our information. Sample mean 98, population mean 95, sample standard deviation is 7 over radical 20. That's 1.92. The value falls in the non-critical region. We do not reject H naught. There is not enough evidence to reject the claim. Number 4 states the following. Foothill Hospital is comparing its performance against an industry benchmark that no more than 50% of normal births should result in a hospital stay exceeding 2 days. There are 31 births in a sample of 50 normal births that had a length of stay greater than 2 days. Alpha 0.05 test a claim that Foothill Hospital exceeds the benchmark. So here we're testing for proportions. The claim is that the population proportion P is greater than 50%. That's H sub 1. H naught is that P is 50%. We have to calculate the sample proportion X over N, so 31 out of 50, 0.62. We compute Q. Q is 1 minus P. P is 0.5, so 1 minus 0.5 is 0.5. And this is a z-test. Whenever we test for proportions, it's always a z-test. We can then calculate the test point. P hat is 0.62. P is 0.5 over radical. P and Q are both 0.5. Divided by N is 50. That's going to give us 1.7. It's a right tail test. Greater than 0.05, one tail 0.05, go all the way down to the z value, it's 1.65. That's our critical value. And then the test point 1.7 is greater than 1.65. It falls in the critical region, thus we reject H naught, and there is enough evidence to support the claim. Number 5, we compare the difference between two means. It states a sociologist wants to determine if the average life expectancy of people in Africa is less than the average life expectancy of people in Asia. And so we're given the summarized data. We use alpha 0.01 to test a claim. Keep in mind that we're given population standard deviations. Thus, we have a z-test. And we're stating that the average life expectancy of people in Africa is less than the average life expectancy of people in Asia. That's our claim. That's H sub 1. H naught is that the two means are equal. We apply the formula. Keep in mind that the difference in the population means is 0. We have the difference in the sample means divided by the square root of each variance squared divided by each sample size. That's going to give us a value of negative 6.86. We look up the critical value in table F. One tail, 0.01, go all the way down, 2.33, and since it's a left tail test, it has to be a negative 2.33. That's the critical value. The test point is to the left of that, so it falls in the critical region. Thus, we reject H naught, and we say there is enough evidence to support the claim. Number 6 states a realtor hypothesizes that the average selling price of a home in the northwestern part of a certain city is significantly higher than the average selling price of a home in the southeastern part of the same city. Alpha is 0.05, test a hypothesis. So we have our data. Once again, we're given sigmas, thus it's a z-test. And the claim is that mu sub 1 is greater than mu sub 2. H naught is that the two means are equal. Once again, we apply this formula, so we compute the difference in the sample means. Mu1 minus mu2 is always 0, divided by the square root of each standard deviation squared, divided by each sample size. That's going to give us a value of 2.88. It's a right-tail test. Alpha is 0.05. One tail 0.05. The critical value is 1.65. So the test point falls in the critical region. We reject H naught. There is enough evidence to support the claim. Number 7 is a similar problem, but we're now given the sample standard deviations. That informs us that we have a t-test. The problem states that a wine merchant wants to determine if there's a difference in the average price of domestic wine and the average price of imported wine. Test a claim, alpha is 0.05. So the word difference means not equal to. So we're saying that mu1 is not equal to mu2. That's the claim. H naught is that the two means are equal. Once again, we plug everything into this formula. Difference in the sample means. Mu1 minus mu2 is 0, divided by the square root of each standard deviation squared divided by each sample size. That's going to give us a value of 2.56. Now, to find the critical value, we need degrees of freedom. So we pick the smaller of the two ends. We pick 14. 14 minus 1 is 13. That's the degrees of freedom. So 13 is our degrees of freedom. It's a two-tailed test, 0.05. We go down 13 to get 2.16 as the critical value. So we have a left and a right critical value. The test point falls in the critical region. Thus, we reject H naught. There is enough evidence to support the claim. Number 8 states the following. The average price of 9 XYZ dishwashers was $845, and the average price of 7 ABC dishwashers was $815. The sample standard deviations were $19 and $49 respectively. That informs us it's a t-test. Alpha 0.01. Can one conclude that the average price of the XYZ dishwashers cost more? So our claim is that mu1 is greater than mu2. H naught is always mu1 equal to mu2. We calculate the test point. We take 845 minus 815 minus 0 divided by the square root of each sample standard deviation squared divided by each sample size. The value for the test point computes to 1.53. We look up the critical value, so once again we pick the smaller of the two ends. We have 9 and we have 7, so we use 7. 7 minus 1 is 6, so that's our degrees of freedom. It's a right-tail test, alpha 0.05. We go down to degrees of freedom is 6. One tail, 0.05, go down to 6, 1.943. That's the critical value. The test point is to the left of that value, thus we do not reject H naught. There is not enough evidence to support the claim. Number 9, we're testing the difference between two proportions. The problem states the following. In a local city, citizens that belong to one of two particular political parties were asked to answer a survey as to whether they would like an increase in local taxes to fund the establishment of a new park in the city. Test to claim that the percentage of Democrats who favor the tax increase is more than the percentage of Republicans who favor the increase. Alpha 0.01. So P sub 1 is greater than P sub 2. That's the claim. That's H sub 1. H naught is that the two proportions are equal. So we have to compute the sample proportion for the Democrats first. 140 out of 200 is 0.7. Then the sample proportion for Republicans is 90 out of 150, which is 0.6. We now have to compute the weighted proportion, so we take 140 plus 90, which is 230, divided by 200 plus 150, which is 350, and we get the proportion 0.657. I'm rounding to 3 places. And then Q bar is 1 minus P bar, so 1 minus 0.657, that's going to give us 0.343. Now we calculate the test point, so we have the difference in the sample proportions minus the difference in the population proportions is 0, divided by the square root of P bar, that's 0.657, times Q bar, 0.343, times 1 over 200 plus 1 over 150. Perform the calculations in the calculator to get 1.95. This is also a z-test, so it's a right-tailed z-test. Alpha is 0.01. One tail, 0.01, go all the way to the bottom to get the critical value, 2.33. The test point falls in the non-critical region. Do not reject H naught. There is not enough evidence to support the claim, is the summary. Number 10 states the following. It says, a study is conducted to determine the relationship between a student's performance on an essay in an English class and his or her performance on one exam in a math class during fall 2019. We have our data and we want to test for correlation using alpha 0.05. So first of all, we set up our claim. It's H naught is rho equal to 0. That's always the claim. And H sub 1 is rho not equal to 0. We draw the R bar. We have to look up the critical values in table I. So we need degrees of freedom. We count the number of pairs. 1, 2, 3, 4, 5, 6. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, degrees of freedom is n minus 2. So 10 minus 2 is 8. We know that alpha is 0.05, so we now turn to table I. So alpha is 0.05, we go to 8.632. So we have positive 0.632, negative 0.632. We want to use our calculator or Excel to compute R. R is 0.969. That's going to fall in the critical region. So we reject H naught, and that informs us that there is a linear relationship. We then find the line of regression for this problem because there is a linear relationship, and we can use our calculator to compute the regression coefficients. So the line of regression is y prime is 0.941 times x plus 4.778. And then we make our predictions. We plug 75 into this equation, and it produces an estimated value for 75. So if someone scores a 75 on their English test, they're predicted to score a 75 on the math test. On to number 12. Number 12 says the following. A study is performed to determine if the hours worked by a student is correlated to the number of absences in classes or of classes by the student at school. Test a claim using alpha 0.05. So we have our data. Once again, H naught is rho equal to 0. That's the claim. Even though this looks like a P, it's actually a Greek letter that represents the population correlation coefficient, and it's called rho. And H sub 1, rho is not equal to 0. We calculate degrees of freedom. We count the number of pairs. 1, 2, 3, 4, 5, 6. 6 minus 2 is 4. We go to table I. 0.05 go down to 4, 0.811. So we have the critical values, negative 0.811, positive 0.811. We calculate R using Excel or a calculator. It's 0.995. That definitely falls in the critical region. We reject H naught, and we state that there is a linear relationship. We then would use our calculator to compute the regression coefficients. So y prime is 0.135x plus 0.925. Make our prediction when x is 10. So if we plug 10 in here, so if a person has so if a person works 10 hours, we want to know how many absences they have. So 10 times 0.135 plus 0.925 rounds to about 2 absences. That's our expected value. Okay, number 14, we're computing a confidence interval. So the final exam may go back to chapter 6. So we're going to review some problems that we encountered in chapter 7. It says the following: a clothing manufacturer wishes to estimate the average price of jeans in the LA region. She samples 50 pairs of jeans and finds the average price to be $55. The population standard deviation is $15. That informs us we have a Z value, and the confidence level is 95%. Estimate the true mean price for a pair of jeans. So we're using this formula to estimate the value. We know x bar is 55. We know sigma, that's 15, and we know n, 50. We need to find the Z value in table F using 95%. So 95%, that's going to be 1.96. We plug that information into the formula, calculate, we get a average estimate. The average is between $50.84 and $59.16. Now number 15 states the following: for a sample of 10 men subjected to a stress situation, the mean number of heartbeats per minute was 126 with a standard deviation of 4. Find the 90% confidence interval for the true mean. And so we're given the sample standard deviation, thus we're working with a t value. So degrees of freedom is 10 minus 1, which is 9, and then we can use 90% and 9 to find our t value. 90% go down to 9, it's 1.833. And then the formula we use is this one here. We're estimating the mean. X bar 126, t 1.833, sample standard deviation 4, and n is 10. We calculate, and we end up with the average of heartbeats is between 123.68 to 128.32. In number 16, we're estimating a proportion. So it states that a survey of 120 freshmen shows that 18 did not wish to work after marriage. Find the 95% confidence interval of the true proportion of freshmen who do not want to work after marriage. So our formula is this formula here. We need to find the z-values. P hat, or the sample proportion, is 18 out of 120, 0.15. Q hat, or is 1 minus p hat, so 1 minus 0.15 is 0.85. At 95%, the z-value is 1.96. We plug that information into the formula and calculate. And so the proportion of freshmen who don't want to work after they get married is somewhere between 0.086 and 0.214. Number 17 is a problem in which we have to compute a probability using the normal distribution. So this goes back to 6.1. It states the following: assume that the heights of all horse jockeys are normally distributed. That informs us we can use the normal distribution. If the average height is 62 inches, that's our average, and the standard deviation is 3 inches, find the chance that a jockey will have a height greater than 66 inches. So we need to find this tail area. That's going to be the probability that we're looking for. Our next step is to calculate this corresponding z-value. 66 minus 62 divided by 3 is 1.33. We look up that value in table E. So 1.30123 is 0.9082. That's the area to the left. We want the area to the right, so 1 minus 0.9082 is 0.0918. Number 18 is a central limit theorem problem from 6.3. It states the following: the average score on the GMAT is 450. So since it's a central limit theorem, we're going to have a normally shaped distribution of sample means. The mean is 450 and the standard deviation is 44. If a group of 34 individuals take the exam, what's the chance that the average of the sample will be between 470 and 490? So we have to find this area. Since we're using the central limit theorem, we have to use this conversion formula. We take 470 minus 450 divided by the standard deviation 44 over radical 35 sample size, 2.69. And then for the other z value, it's 490 minus 450 over 44 divided by radical 35, 5.38. We then look up both of these areas in table E. If we look up 5.38 in table E, it says here, for any z value larger than 3.49, the area to the left is 0.9999. So that's going to be the first area, so 0.9999. Then we look up 2.69. 2.69 is 0.9964, and we subtract that area from 0.999, and that's going to give us a probability of 0.0035. And that's the review. We went over each problem. Obviously, if you have any questions, feel free to email me, but good luck on that final. Take care, and thanks for watching the video.